In this video, I'm going to be walking you through bubble sort, insertion sort, and selection sort. And in the next video, I'm going to be talking through merge, quick, shell, and radix sort. So bubbles, insertion, and selection sort all have the big O notation of n squared, which means they're pretty inefficient for large data sets, but they're pretty stable and they're pretty simple to understand. So they are a pretty good starting point for sorting algorithms. So to start off, I've made a timer that will measure the time from when we first start the program till right after, and it will calculate the elapsed time, and then it will average it for 20 different runtimes of each algorithm. And then at the very end, it'll calculate the average and print it out in milliseconds. So the first sort I want to look at is bubble sort. Bubble sort is a swapping algorithm. It will look at pairs. So it'll look at the first element, it'll compare it to the one right next to it on the right. If the second element is greater, if this element is greater than the next one that you're looking at, you swap them and move on to the next element. And then you check it again. If the current element is greater than the next one right next to it, you swap it. You continue going until you get to the end of the list, and then you come back to the beginning, minus the part you've already checked, and you go again, sorting through all the list, swapping them by pairs. So in the code, it is a nested for loop. So you have one for loop that checks inside. You're going through the list. It will check inside. If the position is greater than the next position, it will swap them. And then you have a bigger for loop that allows you to go multiple times through the list. The next algorithm that I want to look at is insertion sort. So insertion sort is also similarly, it will swap, but for insertion sort, it splits the array into two different sections, sorted and unsorted, and then it will take from the sorted bit and it will take from the unsorted bit and put it into the sorted area exactly where it should be. So it will take each value and it will place it on the left where it would be. Again, this is a nested for loop, similarly to the bubble sort, and you can see that nested for loops often have the n squared big O. So the outside for loop loops through the position, while the inside checks each one on the unsorted bit, and then it will place it into the correct spot in the sorted bit. So if it's smaller than the previous one, it'll take it and again do a swap with a temporary and go to the beginning. And if it's not greater, it will break out of the inner loop because it's in its correct spot in the sorted section. Next, we're going to look at selection sort. So a selection sort is similar. It will split the array into a sorted and unsorted section, and it will take the greatest element from the unsorted section and put it onto the next element possible in the sorted section. And it'll work through like this all the way until the unsorted section has been placed into all of its correct values and the whole array has become sorted. So in the code, your outer loop will go through the array and swapping in the minimum values until it is sorted. And then the inner loop will loop through the array that has not been sorted yet and find the minimum value and update the variable, and then it will place it and swap it again. The next sorting algorithms we're going to take a look at are merge, quick, shell, and radix sort. So in merge sort, it is usually a recursive method that takes an array, and then we looked at the left and the right index. So with a merge sort, we will divide the array up. You can think of it as similar to a binary search, how we split it, so we get the right and the left side, and then the left of the left and the right of the left, and then we keep splitting it down until we get them to individual blocks. Then we compare each individual block to its partner, and then we merge those two together. And then we compare the block of 2 with the other block of 2 and merge those together. And we keep merging until we get to the top level, and at the very end, everything will be sorted. So to do this, because it's recursive, we need a base case. So if the left plus 1 is equal to the right, which means we have an array subset of 1, so we're at the bottom level. If that's the case, then array 1, we create a new array list, we add the left to it, and we return the array 1. So we return the smallest bit. Otherwise, we make a mid, so we have right plus left divided by 2, that would be our middle, and we split it. So we make a new array list, A and B in this case I called it. We call the merge sort again with left to mid and then mid to right for the other array, and then we put together the sorted array. So we make a new sorted array, an A pointer and a B pointer, and integer length, so the size of the big array is the first array plus the second array's length, and then we loop through the array and we add them according to increasing order. So first we check if the A pointer is greater than or equal to a size. So if it's greater than, that means there's nothing left in the A array and we're finished with that array. If not, we add to the sorted array the b.getPointer and we increment the b pointer. So if the b pointer is greater than the size, we add the a. So we add the next element of a and we increment the a pointer. And if none of that's true, we add the smaller value of the 2 using the index pointers we had, and then we increment the pointer to look at the next value of the array. So we compare the a pointer value, the element at a pointer to the element at b pointer, and if the a pointer is smaller, we add the a pointer and we increment it. Otherwise, then that means the b is either greater than or equal to the a, so we add the b, and the b is smaller than or equal to a, which means we add the b and increment the b pointer. And then after all of that, we return the sorted array. So as this works, as you go through this and go through it recursively, it will merge from the bottom up and you will get a final sorted array. Merge sort has the big O of n log n no matter what. It is the most efficient, one of the most efficient sorting algorithms in the set that we're looking at. So the next one I want to look at is quicksort. Quicksort is similar to merge sort in that you were recursively splitting an array and dividing and conquering to sort it. But unlike merge sort, quicksort, you are picking something called a pivot point, and this pivot point is going to be where you're splitting it. So most people use a median of 3 method, but for simplicity's sake, I'm going to be making the pivot to be always the last value, so the right. So in a pivot, in a quicksort, you pass in the array, the left integer and the right integer for the elements, and again you are recursively calling it. So if the left is less than the right, which is the base case, then you call x equals the partition, so you partition it with array left right, which we will go through, and then you recursively call according to the partition that you receive. You call quicksort again with array left and then x minus 1. Because we are not actually including the partition, like the pivot point itself is not being included in our quicksort, we call left and x minus 1, and then the next one we call x plus 1 and right. So the partition function itself returns the index of the partition and sorts the array. So in this function, we take in an array left, right, similarly to the one above. Our pivot will, as I said, will always be the rightmost element. So this makes it a little bit less efficient, but a little bit easier to understand. So the smaller element will be left minus 1, which is I, and then it will loop through the sublist of the array and swap according to the pivot. So you're going through from j, from the left all the way to the right. If the array is less than or equal to the pivot, you increment I, and then you swap the 2 elements. So they get swapped here, And then at the very end, you swap them again, and you return I plus 1. So as you can recall, we started at left minus 1, so the first call would return simply left. So it'll keep going until you've sorted the whole array, and then your final int will return the index of the partition itself. So this will come up here, and then it'll quicksort and call itself because you're calling recursively and then calling a function that's also, you're going to be calling the partition function, which is doing the actual sorting. Quicksort does have a big O of n log n, but this can vary all the way to n squared. Similarly, shell sort also has an n log n big O notation, but can vary worst case to n squared. Shell sort is similar to an insertion sort, but instead of having an insertion sort on the entire array, we're splitting it into sub-arrays and doing insertion sorts on each sub-array. This makes it so that the gap sizes are a lot smaller, and if you have to move something from one end to another, it makes it a lot easier. So here it looks very inefficient because you have a nested for loop with a while loop in the middle, but it is more efficient because of these gap sizes. So you have a for loop which will go to half the array, and it will divide by 2 each time and split it into subparts. And then you will have another for loop nested in that will start at this size and increment, so it loops through each part. It'll set k equal to j, and then inside you have a while loop which will perform the insertion sort and swap them if they need to be swapped. So at the very end, it will return the array. So the last and final array sorting algorithm that we're going to be looking at is radix sort. Radix sort is very efficient. It has a big O of nk, where k is the amount of digits in the largest number. This is very efficient because what it does is essentially it sorts based on digits. So it'll look at the ones column, it'll sort it based on the ones, then it will sort based on the tens, and then based on the 100th place. And if your max only has 3 digits, it's done. So after it has sorted through the 100th place, your entire array list has been sorted, and it only took 3 passes. So how do we do this? First, you create buckets. So I made an array list of a circular linked list. You can use any kind of list or array list or anything like that, called buckets. And I added 10 new circular linked lists because there are 10 possible digits, 0 through 9. And now I have, basically you have a matrix of 10, but it can be as many digits, as many runs as you need to, because it is a dynamic list or a dynamic array list. So then you calculate the number with the most digits. That's basically finding the largest number in the array list. You pass through it once and you find it with a simple comparison, and then you calculate the digits in that number using the mathlog10 method plus 1, and that'll be the number of passes you need. Then, once you have the amount of passes you need, you're going to loop through 3 times, or however many digits you have, you're going to loop that many times and process each time. So, for each run through, you're going to run through your array, you're going to get each value, and you're going to do that value divided by math.pow, so 10 to the power of I, and then you're going to mod that by 10. So this is, you're basically, with D, you're getting the appropriate digit and you're adding X to it. So now that everything has been sorted into its appropriate bucket, you add all the values in the bucket back to the original array, preserving the order and emptying the buckets. So after you do that, you're going to loop through for the second run through, or maybe you only have 1, but if you have 2 or more, you loop through the whole thing again, and you're sorting based on the second digit. So you sort them into their appropriate bucket, and then you add all the values back to the original array, and it preserves order one more time, and you empty all of the buckets. So you keep doing that until you've looped through every run through that you need to get through, and at the end of that, your array will be sorted. So now that we've taken a look at all 7 of these sorting algorithms, we are going to run it. As we discussed, the quick merge, shell, and radix are all substantially faster than selection, bubble, and insertion, so they will be a lot smaller numbers. As you can see, the bubble, insertion, and selection are more than 80 milliseconds for each of them, and these two are pretty high too. But merge, quick, shell, and radix all stay under 4 milliseconds, which is pretty fast. And this is all for the same array list, the same data sets. So those were the 7 sorting algorithms that you can use to sort your data. These all use array lists, but there are also sorting algorithms for lists, for trees, etc.